Okay, and now, okay, no, maybe. So, first exercise, we have a hole. We have an XY coordinate system. And here is the X axis, and here is the Y axis. We have a material point in the origo here. Initial parameters. We have an initial, so we don't have initial velocity, so we 0 equals to 0. We have a given time t1, which is 4.2 seconds. We have a speed of sound Vs, which is 333 meters over second, and there is gravity G 9.81 meter over square second. So here is the G gravity of G in Y direction. A G vector, we have the dimension of the whole, for example, H. So our material point, it's for example a small stone, and we can calculate with it as a material point. So our material point falls down, reaches the bottom of the hole, and the sound comes back with a Vs velocity. So t1 is the time when we hear the knocking of the stone at the bottom of this hole. So the material point falls down, reaches the bottom of the hole, speed of sound comes back, and when we hear the sound, that's 4.2 seconds, right? And we are looking for, what are we looking for? We are looking for H, the depth of the hole. Now, what can we use? What are our common equations? In this lesson, usually we use vector equations. So let's write our equations as a vector scalar equation, but write our equations as a vector. So in general, our common equations, we have an acceleration vector we have a velocity vector and a distance or position vector. It's r, not v, r. So in our case, our acceleration can be, okay, let's write, it can be g, but only in that case when the stone falls down. When the sound comes back, there will be no acceleration, but let's take the first part of this exercise. Stone falls down. Then we have a g vector. In that case, our velocity is the integral of our acceleration, which is in general v0 vector plus g times t. Now we know that v0 is 0, so we can drop our v0. But in general, our v vector is v0 plus g times t. And our position vector, we have an initial coordinate r, more beautiful r0. Now we know that our initial position is the origo, so our r0 will be 0 again, but in general we have an r0 plus v0 times t plus half gt square, or gt square over 2. It doesn't really matter. Now, first part of our exercise. You can see we have a vertical movement. The stone has a vertical movement and the sound also has a vertical movement, so we need only the y coordinate of our parameters, ay, vy, and ry, which can be only y. So first part, when the stone moves. So our ay is minus g. So you can see that y direction is to the top, g has the opposite sign, so ay is minus g. So now it's a scalar equation. Here are the vectors.
Sorry, Professor.
Yes.
This first scenario is when the stone is going down.
Yes. Yes.
Oh, okay. Thank you.
Yes. So the first part is when the movement starts until the stone reaches the bottom. This is the first part. And our first part equations are, we have a minus g acceleration, it's constant. We have a vy function. We know that v0 is 0, so we don't have to write v0. Vy equation is minus gt. Minus gt, and let's write a parameter, not the general t, let's write, for example, tm, like the material points. It's the time of the movement of the material points. So let's write tm here. We don't know tm, we will calculate it. And from the Vy equation, we can write the y equation. So it's the vertical movement function. We have no v0, so v0 equals to 0. We have no y0. Y0 is 0, so we can write only that minus 1 over 2 g dm square. So 0 plus 0 minus this part. Okay, so we just integrated ay 2 times. Our constant parts are 0 everywhere. So these are our functions of the movement of the material point. Second part, sound. What is the situation with sound? Gravity has no effect with sound, so our acceleration is 0. And let's write Ts, like the time for the movement of the sound. Okay, so Tm is for the material point, Ts is for the sound. Okay, after that Vy Ts had it will be a constant Vs, and we know the speed of sound Vs. And our displacement function is, don't forget the y0. What is the initial point of the sound? So we have to write the coordinate, the initial coordinate, this coordinate, into our equation. This coordinate is minus h. So we are under the x-axis with h, so it's minus h. This is our y0 minus h. So this is a y0. Plus the integral of Vy, which is Vs Ts, and there is no acceleration. Okay.
Sorry,
Yes?
I don't really understand why the acceleration equal to the 0. I think the acceleration should have the gravity, I think.
Because in the second part we take only the speed of sound, and gravity has no effect for the speed of sound. It's a constant value, speed of sound in the air. It's constant. There is no acceleration. Gravity has no effect. Other acceleration has no effect to that. Okay? And that's why our acceleration is 0.
Sorry, Professor, if you
Yes?
don't mind, can you please go through the second part one more time?
Yes.
Thank you.
Yes. So, second part. So our material point reached the bottom. Its movement stopped. Okay? So reach the bottom, but the sound goes back to the top. So there is only sound movement. So material points stop moving. Speed of sound is constant. no gravity, so we are in the air. In the whole exercise we are in the air, no water, no other material changes, just one material, air. And in the air, speed of sound is constant. Gravity and other acceleration doesn't really matter. That's why we have in the second part, so first part is to the material point, second part is to the sound.
Yes, Professor, now I get it since you said it's constant.
Yes, so no acceleration effect, so speed of sound must be constant, the constant Vs, and because it's constant, there is no acceleration. Okay?
So this is a sound speed. This process, the second process is alright. I thought it's the reflect.
Yes.
Okay.
And we integrated this Vy, and we got our Y function. But into the Y function, we have to take into account the initial position, the initial coordinate of the speed of sound, or sound speed. So the movement started at -h. So our y0 is -h. Okay. And the integral of the constant Vs is the Vs times t. And that's all. Now we have many equations. And what are we looking for? We are looking for h. So we are looking for the depth of our hole. What we can do?
And I think Tm is T1, right?
No, T1, yes, good idea. T1 is the sum of Tm and Ts. So not sum, equals to. So, when we start our clock is when the material point starts moving, and we stop our clock when we hear the sound. So T1 is the time, sum of the time of the two movements, the material point and then the sound. So T1 is Tm plus Ts. That's what we know. That's okay. What we know. What we also know that. So in the first part we wrote our equations for the end of the movement. So we wrote our equations to this point at the bottom of the hole. And because of that, we know the position, the end position of the material point. So we know that YTM is -h. So our end coordinate when the material point movement is ended is at -h under the x-axis at h. So, and we can write now, and also we know, the ending position of the sound. So we hear the sound. We are standing at the origo. We dropped the material point from the origo to, so from the 0, 0 point, material point is dropped, sound goes back, and we hear the sound at the origo. So we know that we hear the sound at the 0 y value. So our let's write it again. Our position equations. Let's write it. This is first. This let's write this way. This is the first, and this is the second equation. What we have to use. So our first, yes.
Excuse me. So the YTS is equal 0.
YT. Sorry, YT.
The S, the YTS. I mean the
is
second
0.
point.
So we hear the sound at this point. We are here. We hear the sound at this point, at 0.
Okay. Okay. All
so
right.
the coordinate of our position where we hear the sound is 0. Now, first equation. So our y coordinate at the end of the movement is -h. And our equation is -12 g tm square. And where we hear the sound, it's 0. And our equation was -h. So the movement started at -h coordinate plus VSTS H. Okay, so we have two equations, and we see that -h is this value, and we see -h in the other equation. So we can write the -h value, this value, into the second equation. Let's write this. So first, from the first equation, we know -h is -1/2 g tm square, and we can see -h in the second equation. So write it in it. So 0 equals to -h, which is -1/2 g tm square plus the VSTS, and we know
Professor, that should be plus, right? The value of -h. No, yeah, it's okay.
minus. So yeah, that it seems that's right. But so here is Tm and Ts. But we know that T1 equals to Tm plus Ts, and we know T1. So we can write, for example, so rearrange this equation, for example, to Ts, but you can rearrange it to Tm, it doesn't really matter. So I rearrange it to Ts. So from the time equation, we know that Ts equals to T1 minus Tm. And I can write this into our equation. So 0 is -1/2 g Tm square plus Vs times Ts, which is T1 minus Tm. And now there is only one unknown parameter in our equation, Tm. It's a quadratic equation. I hope you can solve a quadratic equation, so don't waste time for it. From this quadratic equation, we can get 2 Tm. The first Tm is minus 71.858 seconds. There is no sense, so we cannot use a minus time. So that's sure that this is wrong. This is wrong. And our second Tm from this equation is 3.968 seconds. So from this equation we got that the material point reaches the bottom of the hole in 3.968 seconds. That's Tm. And we can calculate Ts from here. But no, it doesn't. We don't need Ts. But if you would know, you can calculate Ts. From Tm, now we can calculate H from the first equation from here. So now we know Tm, G is an initial parameter. So from the first equation we can calculate H. So minus H equals to minus 1 over 2 GTm squared. So H equals to 1 over 2 GTm squared. So I multiplied by minus 1. And from this H is 1 over 2 times 9.81 times 3.968 squared, which is 77.229 meters. So this is the depth of our hole. Okay?
Sorry, yep. Professor. Above the 3.968, that is 71.858. What is that? I don't understand.
So here is the equation.
Yeah.
Yeah, you can write it in. So you can order this equation. So it's 0 equals to minus 1 over 2 GTm squared. So we have a quadratic parameter plus Vs times T1. It's constant. We know Vs, we know T1. So it's a constant part. And plus Vs times minus Tm. So minus Vs Tm. So this is the first ordered part of the Tm. So this is a quadratic equation you can solve, and you have to get two values from this equation to Tm because it's a quadratic equation. In this case you got, for example, Tm1 or Tm and Tm2. In this case you got a negative value and a positive value to Tm.
I understand again.
Now we can, so it doesn't make sense that the time is negative, so the minus 71 value, we are sure that it's wrong. so time cannot be a minus. So our second value must be the right value. Okay. Another question?
Yeah, Professor.
Yeah.
Can you explain shortly why T1 equal Ts plus T?
Right here.
Yeah.
Here, T1. So our initial value was T1, which we know that from when we dropped the material point, from that point and until we hear the sound of the knocking at the bottom. This is the time interval T1, which is 4.2, and there is a movement of the material point has a time. We don't know what, but it has a time Tm, and sound has another T time value when the sound reaches from the bottom the top point where we are and where we hear the sound. So Tm is the time parameter from our initial point, from where we dropped the material point until the material point reaches the bottom. Ts is from the bottom to top when we hear the sound. And our initial parameter was the sum. So it was defined like it's the sum of the two parts. So the sum of the time of the movement of the material point and the movement of the sound. Right?
Yeah, I think I got it.
Okay.
Thank you.
Okay, let's jump to the second one. Second exercise. Second exercise. Okay. We have an acceleration diagram. AT, A in meter over square second, T is in second. And our diagram looks like this. So the diagram has also two parts, two sections, first order section and the constant section. We know the constant acceleration value A1, and we know T1 and T2. So we can split this exercise into two parts, first section or first part and the second. So the first, in the first section we have a first ordered or a linear function, and in the second part we have a constant function. And we know other parameters, so we know that our initial time is at 0, so t0 is 0. We know that we start at the origo, so our s0 is 0. So we are looking for, from the acceleration function, we are looking for a velocity function and a v velocity function and an s displacement function. And we know that our initial time is 0, our initial position is 0, and we know t1, it's 2 seconds, we know t2, it's 6 seconds, so we know every t parameters, t0, t1, t2. We know S0 is 0, we know A1, which is 4, and we know V2, which is 24 meter over second. And we are looking for S2, so the end point of our movement, or end point of our displacement. We can draw a coordinate system for the velocity and no, not x, sorry, it's t. So we can draw a VT coordinate system. We know t1 and t2. We know what we know V2. For example, here. So we know the velocity parameter at t2. And that's all, unfortunately. And we can draw a displacement coordinate system, an ST coordinate system. S in meter. T1, T2 also known. And we know the S0. Great. S0 is 0. So we know S0, we know V2, and we know A1. And so determine S2 and draw the VT function and the ST function. What we know? We know that the VT, so the velocity is the integral of the acceleration, and we know that displacement is the integral of velocity. So, and we have two sections again, so we have to split our exercise into two sections. So in general, what we know, we can write the constant variation of these functions now. So we know that we have an acceleration, we know that the velocity is the integral of the acceleration, and don't forget the constant part. T0 now it's 0, and we know that displacement is the integral of the velocity. Let's write our equations in these in two ways. So in the first way, use these equations. And let's take into consideration the first part now. Now that in the first part we can see a linear function, so we have to write a linear function equation as an acceleration function. So first function we check that where is the what is the a value at t0. Luckily it's 0, so it means that there is no constant part, and we have to write only first order function. So our depending value is t, and what is the from what we have to multiply t? We have to multiply the tangent of this angle, and this is our first order equation. Okay, so our constant part is 0, so our t0, our acceleration value is 0, and so we have a linear function, and a linear function must be a tangent angle, so tangent alpha times t, and that's all.
It's A1 over T1.
Yes, and we can write tangent alpha as A1, so the opposite side of the alpha angle, A1, this is A1. And what is the next to alpha? This is T1. So tangent alpha we can write A1 over T1.
Professor,
Yes?
can we use Pythagoras theorem directly on that triangle?
If it gives perfect value, then of course.
Okay.
So the method doesn't really matter. I like this tangent alpha method, but what is comfortable for you. So our function in the first section is a1 over t1 times t. We have to integrate vt. We know v0 probably is not 0, so let's take into account v0. This is the constant part, and we have to integrate at, so plus a1 over t1, it's constant, we just write it, and the integral of t is t squared over 2. Okay, and we have to integral again for s. what we know that S0 is 0, so we can drop S0. This is the constant part plus the integral of the v function, so plus v0 times t and plus a1 over, okay, let's write a1 over t1. T square must be integrated, so it's t on third. We have the 2 over 2, and the integral of t square is t on the third over 3. So we have to find. So this is the integral of t square. Okay. This is the first section. This is for the first section. Second section. The second section, we know that we have a constant a1 value, so it's easier than the first section. So in the second section, the acceleration is constant a1. That's all. Vt. The initial value of the v velocity function in the second section is v1. So don't forget that we are here now between the two blue lines. So when the velocity reaches t1 and at t1 it reaches v1, so don't forget that the second section's initial velocity value is v1. So as an initial constant, we have to write into our velocity function v1. v1 plus the integral of the acceleration a1 times t. And the displacement, same situation. So the s value reaches something at the end of the first section, S1. So the first section's endpoint is the initial value of the second section. So when we are between the blue lines, our initial value is S1. So that's the constant part what we have to write into our equation, S1, and plus the integral of the velocity function v1 times t plus 1 over 2 a1 t squared, or a1 times t squared over 2. It doesn't really matter. Now we have so many equations again. We have 1, 2, 3, 4, 5, 6 equations. And what we are looking for is the S2. So write the concrete time parameters into our equations. So we know that our first section starts from t0 and ends at t1. So our time parameter, our time interval in the first section is t1 minus t0, which is t1, because t0 is 0. And in the second section, our time interval, our time parameter. The first section's initial time value is t1, the end point is t2, so our time interval is t2 minus t1. So first section, time interval t1 minus t0, second section, time interval t2 minus t1. I hope it's right. So let's write these concrete time parameters into our equations. Yeah, okay. So first equation, we know that so at the left side let's write the values at the endpoint. So at1. So the acceleration at t1 is a1. We can see here. So we can write a1 instead of at1. And we wrote our function a1 over t1 times t1 minus t0, but t0 is 0, so we can write only t1. And as you can see, this means that a1 times t1 equals to a1 times t1, so it's not really useful. So we can't use the first equation. Second one, so the endpoint at the first section, so v1, so at t1 our velocity reaches some v1 value. So at t1 our velocity is v1, and it was v0 plus 1 over 2 times a1 over t1 times, we can write t1 minus t0 or just t1 instead of t. So we have a concrete time value, so we can write it instead of t. And now we can simplify by t. So you can see a1 times t1 square over t1. So we can drop t1 over t1. So our equations, our second equation is, let's write under this. So our second equation is v1 equals to v0 plus a1 times t1 over 2. Or you can write 1 over 2 times a1 times t1. What is best for you? So we have useful, it seems it can be useful, but we don't know v1 and we don't know v0. We know a1 and we know t1. We have two unknown parameters, but maybe later it can be useful. Third equation with concrete parameters. S1, same game again. At t1 our displacement reaches some value, s1. At t1 it reaches s1. So we can write s1. Our s0 was 0, so I don't write the s0. So I can write v0 times t1 minus t0 again. So I can write t1 because t0 is 0. plus what was the origin? V0 T1, I hope I wrote T1, A1 over T1 A1 over T1 times it was T square over 6, but I can write T1 square, so T1 minus T0 square exactly, but I can write T1 over 6, so that was the 2 times 3, so I can write 6. And we can simplify by T1 again. So we can write that our S1 value from the st function is V0 times T1 plus A1 times T1 square over 6. Also seems useful what we know. We don't know S1. We don't know V0. We know T1. No A1. Yeah, sorry. No A1. No T1. No 6. Okay. Also 2 unknown parameters. Let's go to the second section. We were not so lucky at the first part.
Sorry, Professor.
Yes?
Why don't we put the A1 and T1 to the 1, 2, 3 formulas? Why don't
we will write it, but now let's stay only with these parameters. Later we will write
Okay.
the exact value into the equation.
All right. Okay.
Okay, second part. Our fourth equation. In the second section, we have a constant A1 value, so our fourth equation seems like A1 equals to A1. Not really useful again. Let's see the fifth equation. Our endpoint in the second section, V2. So the endpoint in the second section, the velocity reaches V2. And our initial value in the second section was V1 plus it was A1 times T, and instead of T we can write T2 minus T1, so we have to write the interval value. So we have to write this value into our equation. This is the second section time interval, T2 minus T1. Okay, what we know? We know T2, we know T1, we know A1, we know V2. We have only one unknown parameter, so we can use the fifth equation for something, but let's finish our equations. Sixth value. So at the end of the second section, our displacement reaches S2, and our initial value was S1, so the initial value of the second section was S1 plus V1 times T, I hope, yes, and T The time interval in the second section is t2 minus t1 and plus 1 over 2a1 and times t square, which is t2 minus t1 square. Okay, so we dropped the concrete time values into the t parameter, so we wrote t2 minus t1 instead of t everywhere, and in this concrete t2 minus t1 time interval, we reached S2 value somewhere here. Now what we know, our result should be S2, so we don't know S2 and we are looking for S2. We know, unfortunately we don't know S1 and we don't know V1, but we know T2, we know T1, we know A1, we know 1 over 2. Okay, 3 unknown parameters in the sixth equation. Okay, so let's start with the fifth equation. We can see that we have only one unknown parameter, V1. We can calculate V1 from this. And what we can do after that, when we know V1, then we can use the second equation. We can calculate V0 from the second. When we know V0, then we can use the third equation. We can calculate S1. And after that we can calculate S2. Oh, okay, a bit long, but maybe I can show you a bit shorter and easier method, but we are at the university, so we have to use differential and integral methods also, so let's use these equations. Now, fifth equation, our unknown parameter is V1. So from the fifth equation, V1, it is V2 minus A1 times T2 minus T1. So I dropped the acceleration part to the other part, to the other side. Yes, V1 equal V2 minus A1 T2 minus T1. Okay. And now we can write every concrete value into our equation. V2 was 24 minus A1 is 4, and we know it 6 minus 2 is 4, that A2 times our t interval, it's 4 times 4, and it's 8 meter over second. So we calculated V1. Okay, in which was the second, in the second equation there was V0 and V1, the unknown parameters, and now we know V1, so we can use the second equation, and we can calculate V0, which was V1 minus 1 over 2 times A1 times T1. Okay, substitute our values. V1 was 8 minus 1 over 2 times A1 was 4, T1 was 4. Sorry, 2, T1 was 2. So V1 is 8 minus 1 over 2 times A1 was 4, T1 was 2. Okay, I think we are right, and from this V0 is 4. Now we know V1 and V0, so we can use not the sixth, but the third equation. S1, yes. We can calculate S1, which was V0 times T1 plus A1 times T1 square over 6. I hope, yes. And V0, now we know it's 4 times T1, it's 2 plus 4 times T1 is 2, 2 squared over 6. And from this S1 is 10.667 meters. And now we can use the sixth equation from where we can calculate our result S2. It was S1 plus V1 times T2 minus T1 plus 1 over 2 A1 times T2 minus T1 square. Now we know S1 10.667 plus V1 it was 8 times T2 minus T1 is 6 minus 2, it's 4 plus 1 over 2 times A1 is 4 times 6 minus 2 is 4 again. From this we know S2 is 74 times 667 meters, and this is our result. Okay, so we have seen that when we use the integrated form of our equation, so we integrated the acceleration and we integrated the velocity, and from this equation, so we got so many equations. We can use we could use 4 equations, and this was a bit long and a bit difficult method. So let's see another a bit easier method from we can calculate our key points, unknown key points, for example V1, S1, S2, and we can draw our functions. We can calculate our key points again. We can calculate our key points and we can draw our functions. So let's see what can we do. What is a bit easier and shorter method. We know, okay, we know A1, T1, T2. Sorry, we know V2, we are looking for V1, and we are looking for V0. Don't forget that it wasn't mentioned that V0 is 0, so we are looking for V0 also. And what is an initial parameter that S0 is 0? That's known. And we are looking for S1 and S2. Sorry again. So, what is our method? What we know? We have seen that we have to integrate our function. And what is an integral? In general, an integral in general is area calculation. And we can see here in the AT function, we can see two areas, a triangle and a rectangle under our functions. So when we calculate in the first section the area of the triangle and the area of the rectangle, then we can get the value of the distance between our initial and endpoint values. Let's start the calculation with the second section in this case. So let's see what we can see in the second section in the AT function. It's a rectangle, and the area of this rectangle, which color should I use? The area of this yellow rectangle is A1 times T2 minus T1. Okay, A1, T2 minus T1. This is the area of the rectangle. This means that the distance between V1 and V2 is this area value. Let's write, I don't know, A2. So the area of the second section in the AT function, let's write it A2, is A1 times T2 minus T1. Pretty easy. The area of a rectangle. This is the distance between V2 minus V1. So we know V2. V2 is 24. We calculate A2. I didn't calculate it, but V1 was 8. Yeah, sorry, 24. So V2 was 24, and A2 should be 16. A1, 4. 6 minus 2 is 4, so 4 times 4 it's 16. A2 is 16. So we know V2 is 24. We have to go back A2 value, so we have to go back 16. So from that we know that V1 is 24 minus 16, it's 8. And that's all. First section, the area of the red triangle. Let's write A1, so the area of the red triangle. It's A1 times T1 minus T0, so it's T1 over 2 because it's a rectangle. So the area of this rectangle is 4 times T1 was 2. 4 times 2 is 8 over 2 is 4. So we have to go back from 8. We have to go back 4, we have to go back A1. This is the distance between V0 and V1. So we know that V0 is 4. That's all. What is the shape of these functions? So we know that the velocity is the integral of the acceleration. So let's start with the second section again. So we know in the second section we have a constant acceleration function, so we have to draw first order velocity function. It's a straight line, sorry. So it's a straight line, not a parabola, not everything. It's a straight line, first order function. And this is the shape of the function. We determine V1 and V2. We know V2, we determine V1. First section, we can see linear function. The integral of the linear function is a second order. It's a quadratic, parabola quadratic function. So we have to draw parabola in the, so it's a parabola. Straight line in the second section. Okay, that you have to know that that the velocity is the integral of the acceleration and the displacement is the integral of the velocity. You have to know this because of the function drawing, but after that you can calculate the areas and then you can calculate the unknown parameters. Okay, I started the recording again. And this is the the method is the same between the velocity and the displacement. So you have to calculate. So let's start with the second section again. You have to calculate the area of this trapeze or trapezoid. You can calculate indirectly, or you can calculate the area of this trapeze that you split it into a triangle and a rectangle and sum the area of the triangle and the rectangle, which is comfortable for you. You can calculate directly. It's really useful. Then there is a trapezoid. Usually it's drawn in this way, but now we can see rotated by 90 degrees. So now you see this trapezoid. It's 90 degrees, 90 degrees. Here is a, for example, don't be now you can see it's V1 and V2. let's write it. Doesn't really matter the name of the parameters. Now you can see v1 and v2, and the horizontal side is t2 minus t1, and you can calculate the area of this shape is in this way: v2 plus v1 over 2 times t2 minus t1. This is the general, indirect calculation of the area of a trapeze. So you can write, I don't know, B, D, E side, then the area is B plus D over 2 times E. So in general, but as I mentioned, you can split into two parts, a triangle and a rectangle. You can calculate the two areas and then sum up. Doesn't really matter. Oh, okay, almost the end of the lesson. So let's calculate the area of this triangle. This. Okay, don't calculate, I haven't calculated it, so I don't know what is the area of the shape. So the area of the triangle is the distance between S2 and S1. Sorry, not triangle, trapeze. Area of, I try to draw a trapeze, area of this trapezoid or trapezoid is the distance between S2 and S1. And then the distance between S1 and S0 is the area which is under the parabola. Let's write AP, like area under the parabola. You can calculate, now you must split this area into two shapes. You can get a rectangle here, and you can get a shape under a parabola here. The shape, area under the parabola here, and the area under the parabola is a rectangle. You can draw a parabola in a rectangle, so you see this shape. This is the initial point, end point here. So you can see this shape here. Parabola, horizontal side of this rectangle, vertical side of this rectangle. Calculate the area of the rectangle. Don't write a in general, let's write in general, for example, BC. I don't want to write A because you can mix it by the acceleration. So let's write A instead of B, let's write B and C. The area of the rectangle is B times C. So the area under this parabola is the 1/3 of the area of the rectangle. Okay, so when you can see a parabola like this, you can draw a triangle around the parabola, calculate the area of the parabola and then divide this value by 3, and that this is the area under the parabola. Okay, so you can calculate these area values, and then you can get the distances between the key points. And you can, after that, you can draw the shape of the diagrams. In the velocity function, you can see in the second section a first order function, a linear function, a straight line. So you have to draw quadratic parabola here, and in the first section you can see a quadratic parabola, so you can draw a third order parabola or third degree parabola here. So it's a third order or third degree parabola, and it's a second order or second degree parabola. And that's all. Okay, this exercise. So we finished this exercise, and we want to begin another one. So this is the end of the lesson. Do you have any questions?
Sorry, sir, I want check the final result again.
Final result S2.
Yeah.
We were looking for S2, as I remember. S2 here. 74 times 667.
And the parabola area, can I have a look again? The downside?
Parabola area?
Yeah, that area.
Here.
Okay, thank you.
Teacher, could you upload it like on the e-learning, this note?
Yes. Yes.
Okay, thank you.
Thank you very much.
Thank you so much,
Okay,
Professor. Have a good
you
day.
have no other questions, then
Thank you.
thank you again. And no, switch back to Teams. Oh, yeah, here. So thank you again, and see you next week.
See you.
Okay,
Goodbye.
Bye.
Bye-bye, Professor.